let's see. Let's first of all recall where we left off last time. So this is about the choice of Taylor-Walsh primes. Okay, so here's the theorem. So suppose that, let's see, suppose that I have a row bar. So all the notation as before, F is number field and S is the finite set of places. I'm just going to do it for GL2 for this theorem. And you can kind of imagine what the generalization might be, but not, I guess, precisely. So this is absolutely irreducible. Oh, actually, sorry. I needed to make a correction before that. Thanks to Richie by pointed out to me. So whenever talking about deformations with fixed determinant, I need a condition. I always need to assume that L does not divide the dimension of the representation N. This is because once you have this, the adjoint representation really splits as a direct sum of the sort of trace zero part and the trivial representation. I do need this condition here. Okay, so why is that? So let me sort of, this is because, so let's talk about two things to kind of realize trace zero part. So one of them is sort of trace zero. The other one is this modulo the scalars, right? Right, you can either, I mean, just think of matrices, right? You can either take the trace zero matrices or take the set of sort of space of all the matrices, but then you quotient out by the diagonals as vector spaces. So these are somehow two sort of obvious realizations of sort of trace zero, I guess, in our mind. But then this map in general may not be, this map may not be isomorphous in general. Just think about this. So suppose you have this matrix 1 here. Definitely it will map to 0 because it's scalar. But on the other hand, this trace is what? The trace is equal to N. But if you're L divide N, then this trace could be 0. So this is 0 if L divide N. So that's that. In the sense that in that case, somehow this is not you won't be able to get a direct sum. So there will be some sort of filtration. You can choose it either way, but and this will affect how how one interprets the deformation, the tangent space of deformation, where I somehow have this sort of H1 of the Galois group or gamma of adjoint circ. But that's really, when I wrote this, I really mean that we'll have some sort of direct sum decomposition. In general, this is a bit more subtle if L divides it. But luckily for our application, our N is 2, so as long as L is odd, we're good. Okay. So that's why we're gonna assume from now, for this particular question we discussed, L to be greater than equal to 3. So so in the original theorem, there's a stronger hypothesis. Sorry, in a weaker hypothesis. Let me write that down. So assume that rho bar, when you restrict to the following Galois group, if you take the Galois group of F adjoining this thingy, so -1 to the L minus 1 over 2 times L. So this is a quadratic extension of F. If F doesn't contain this number already, this is absolutely irreducible. This is to rule out some really bad cases where, roughly speaking, if the image of rho bar is large enough, this is satisfied. For example, guess. One of the conditions we're going to impose today to make things work well is that I want to assume that the image of rho bar contains a conjugate of SL2 FL for L greater than or equal to 5. If the image contains an SL2 FL for L greater than or equal to 5, we know that's sort of at least contain a large simple group inside of that. So therefore, I mean, this restriction must be absolutely irreducible. So this is sort of some group theory thing. But in fact, when we prove this theorem today, right, using an argument, we're going to assume this assumption instead of this assumption. The only difference is that when we only assume this, we have to separate several cases by classification of subgroups of sort of GL2 and then discuss each case by case. I figure somehow maybe just to see the picture of the proof, I mean, maybe just assume this stronger hypothesis, making the proof a little bit shorter. General case, just basically a case-by-case argument, not particularly sort of interesting. So, yeah. So, no, but like, I mean, like, you can put S here, if you want to put S here. Of course, if you're restricted to a, so this is a subgroup of GF. This is an extension of F, so this GF, whatever, is a subgroup of GF. It will factor through the parts where it's sort of unramified outside of S. But still, absolute irreducibleness, whether that's absolutely irreducible or not, depends only on, I guess, what the sort of this group, but not sort of. So I mean to say this fact. Oh, okay. Maybe not very rigorous. So F, if that makes you feel better. It's the same thing. Whenever I write this, I can think of it also think of this as a representation of GF by composing. Yeah, it's the same thing, right? And maybe for this condition is not very important. So that of this is cyclotomic. This is probably our application, but I mean I can fix. So then I will lift it to a chi. Just use cyclotomic to lift this determinant. But this is not so important. You can fix any central capture if you want. So let T denote the relative cohomology, which is also the same thing as H as 2 by Euler characteristic. Then for each n, there exists a finite set of places, and we call it Qn. Such that the following three conditions hold. Let me maybe write it on the right-hand side so that I will have some space to work on while keeping these conditions here. So first of all, for each place in the set, the number of elements in the residue field is congruent to 1 modulo p to the n, or the QV. And second, or maybe I should say this this QS is disjoint from my set of flat places. The way I find QS will be via Chebyshev density, so I can always avoid finding many primes. So therefore, because this, I guess because each of the V does not belong to S, the representation rho bar must be unramified at these places. So I can talk about the Chebyshev Frobenius. The Frobenius is sort of diagonalizable with two eigenvalues, and they are not equal. It's not equal. Or you can say alpha bar v squared not equal to 1, whatever you like. Thirdly, the third condition is that, so this R rho bar. So recall last time that we have this, covering this, we have this sort of universal deformation ring with frame at S and determinant chi. But when I put this Qn here, this is sort of frame, it's a deformation of rho bar. But I think of this as GF allowing ramification at these Qn's, and then use this rho bar, GL2F, and frame that at S. I don't put frame on these sort of additional primes Qn. And this is a quotient of so-called R log, local deformation ring, X T. And one of the key points is that this set of Taylor-Watts primes, so-called, these have exactly T elements, being the same T with its sort of dimensions. So last time we spent a lot of time to discuss what this third condition means under the this first two conditions. On the nose, this is equivalent to the following map being an isomorphism. Just right here. So this is equivalent to the following restricted map. Plus this map to okay. Recall that this H1 is original tangent space for this deformation without allowing ramification at this Qn. And this is a deformation space where you do allow some ramification at these Qn's. And this map is an isomorphism. So that's an equivalent way of saying this the third condition. So last time we kind of discussed that. And we spent a length of discussing another way to interpret this, which is kind of on the dual side, showing that this is equivalent to the following, that H1 of GFS without the relative version of the adjoint representation 1, restricting it to be in Qn of H1 of the residue field as this thing. So last time we said each of one of these is F, and both sides are, and it turns out both sides are T-dimensional vector spaces. Because over here you have T elements. And this isomorphism is equivalent to this being an isomorphism. So last time I spent sort of a lot of energy, a lot of time sort of explaining, going through the diagram chasing to show these two are equivalent. So the goal today is to find these Qn's. So find these primes in Qn such that this is okay, and both 1 and 2 are both okay. So in some sense, each one of the condition can be sort of understood using Chebotarev density, or like you can choose some prime to make sort of 1, 2, or this hold. Somehow the tricky thing is to make sure that you choose these primes so that sort of all of them hold at the same time. So today, prove the existence using Chebotarev density. Okay. So what do I need to show? In fact, what I need to show is the following. So for 1 and 2, it's just a question about each sort of individual prime. So basically, I want to make condition 3 about each individual prime. So I claim that suffices to prove the following. Suffices to show that for every basically, let me say, basically at this point, we don't quite need much of sort of what this Galois representation is, or we don't need any sort of Galois cohomology computation. All we need is that somehow this thing has a large image. That's the only input we need. So that's somehow what this sort of this condition comes in, and other things are standard. Okay, so for every class, let me call it C, which is not zero in this Galois cohomology. It's H1 of something. Or I need to show that I can find infinitely many places V such that, first of all, because of the space issue, let me that's okay. Let me write it this way. 1 prime. Because I want to move it over there. Right? I wanted to satisfy the oh, sorry, modulo L to the n. This is killing me. L and T. My bad. Coefficient is L. Sorry. And secondly, all I want is rho bar of Frobenius at V has distinct eigenvalue. As stated. And thirdly, I wanna, so whenever I have a first column of the global Galois group, I can restrict it to the local one. I don't need much. I just wanna, if your global column group, your element in the global Galois column is not zero, when I restrict to this prime V, this is not zero. Okay? When I restrict to this place V, it's not zero. So you should imagine probably this global Galois cohomology, this class, will probably have many local places where your restriction is not zero. And of course, you have to make sure that all these places, among them, you can find some places where the residual, I guess, sort of this number of kV is common to 1, and for me to have distinct eigenvalues. So that's all we need to do. Just quickly remark, once it's done, so I will get, I'll get sort of H1 of the global one. I guess I'll just choose a basis of this one. I'll just choose a basis of this space. It's t-dimensional vector space, which can be computed. I think we did last time. This is t-dimensional. And we just choose a basis. And for each element in the basis, I apply this statement here. So I get a V. So then the restriction of that to this will be, actually no, it doesn't work that way. Let's see. Another argument. Another argument. So once it's done, I get, so let's do this. So I map this to some, so once it's done, okay, I pick an element. It's a bit long to write, so let me just say how I do this. Okay, so I pick a non-zero element in here, right? So by this argument, I get a V. Okay, great. I get a V1. I get a V1 so that, so I pick, first of all, pick a element, say C1 inside of here, not zero. So I get the V1 such that this restriction is not zero. Good. So therefore, I put that V1 into the set. Okay. Now I have this thing. Okay, this is t-dimensional. This is mapping non-zero to a one-dimensional space, so it must be surjective. So then the kernel is now t minus one dimensional. So in that t minus one dimensional space, I pick another C2. Right? I pick the C2 there. And then run this argument again, I get a V2 here. Then I just continue. H1 KV2 of R joint. And of course, the new element will map 0 to here because it's in the kernel. And it will map non-zero over here. So therefore, this, again, is surjective. And the kernel of that is going to be t minus 2-dimensional. And in that t minus 2-dimensional space, I pick another C3 and then get a V3 and so on and so forth. I do it t times. I will get an isomorphism. I choose my sort t primes that way. Okay. So basically, I need to do some sort of universal statement that for every class in here, I can find a local place such that the restriction of this is not 0 and satisfy the first two conditions here. Okay? So let's do this. Right. So let's rewrite this a little bit. I have to be honest with you. I haven't quite understood how this is. I haven't sort of understood it to the point that I understand it internally. So let's just write down their argument. So let's first of all write D to be an extension of F. I think it was 1 here. So let's write D to be this field. What is that field? Well, this is, remember that you have your F here, right? You have your algebra closure F bar here. So that this Galois group is precisely the image of the adjoint representation. If you look at sort of adjoint representation, if you look at your adjoint representation, it's a right? Anyhow, it's a representation of GF to, say, GL to F, right? This has a kernel. And this kernel, you take the subfield of F bar fixed by this kernel. So this is the kernel of adjoint circ 1. And this get cut out the field D, such that I guess this Galois representation will factor through the Galois group of D over. So this will factor through Galois group of D over F, and so. Okay, so that's precisely what the Galois group is. And okay. So step 1. Let's see. Maybe let's do a technical step. Okay. So let's do this to hang there. So this is a rather technical step. I want to show that the Galois group of this from D. Oh, maybe I put it F bar here. Okay. So what I want to do is, on the other hand, I want to talk about F of zeta L to the n, adjoining L to the nth root of unity to that, and this is D adjoining zeta L to the n. Okay. I claim that if I take the Galois cohomology of this one over this for this adjoint representation, that H1 is 0. Maybe I'll come back to prove this in a bit. Okay. So let me prove later. Okay, this will use this big image condition. I want to give you some motivation why I want to do this before proving it. So maybe let's do step 1 later. So once you have this, so suppose you have this, then we have the following inflation restriction exact sequence. So I want to, so the middle term I'm interested in is this guy. Or rather, I mean, like whenever you have H1 of GFS adjoint circ, you can sort of inflate it to its class in here. Okay? So whenever you have this class in here, you can view it as a class in here because I guess this is a quotient group of this one. So you know what's its valuation on these quotients, and you just pull back the cycle, cocycle here. And this, when I look at this sort of Galois group of F, I want to sort of decompose it with respect to sort of F bar to this one, and then this thing to here, to consider the corresponding restriction inflation exact sequence. So I guess what can I do? So I can do H1 of, so let's write that down. So that's d zeta L to the n over F of I joints. Well, supposedly I have to be fixed by the Galois group of d zeta n L to the n. Okay. And let's write down what we have here. So on the quotient, I have H1 of the Galois group of d of zeta L to the n of this I joint representation. And supposedly together I have, I do need this, so I need the Galois group of d. Okay. The inflation restriction exact sequence. So we suppose we have 5 terms. I just need 3 terms. Okay. So I take the subgroup and take the invariance of the subgroup, and then take the first coefficient of the quotient group. And the quotient term here is I take the first Galois coefficient of the subgroup and then take invariance under the quotient group. Now we point out that because the way I take my D, this is a So this subgroup, this is a subgroup of this one. And the Galois group of this D acts trivially on this representation. So it's a subgroup. So this really acts trivially here, so I don't have to write this, because this action is trivial. And the reason I want to do the step 1 is sort of as I said, it's a technical thing, is that I want to make sure that this is 0. So that this map, let's say I want this map to be injective. Okay, so what we were doing here, put it another way, is that, okay, well, let me just write one more step and then explain, sorry. So now we know my C is not 0, so therefore its image in here, again, I want to think of it as C, which is not 0. Right, its image, because it's injective. I need injectivity to make sure my image C in here is not 0. Now when we get to here, as we said before, this Galois group acts trivially here. Therefore, H1 is the same thing as Hom. It's group homomorphism. So I get a group homomorphism invariant under that Galois group. So Galois group of D zeta L to the n over F of this Galois group, comma. I guess sort of equivariant, I guess some sort of C can be viewed as an equivariant homomorphism from this Galois group to here. Because H1 is just Hom. There's no twist action in some sense. So here's sort of a general philosophy of sort of how to prove something like so. So when you have some class in H1, and you want to show there's some sort of local places where the restriction is not 0, the way this is proved is that I want to realize this H1 as some sort of homomorphism. I mean, H1 is not, I mean, if the Galois action is not trivial, H1 is, how should I say it? It's not really a homomorphism. But if I restrict to the subgroup where the action is trivialized, then this H1 class will represent a homomorphism, and so. But before doing that, we have to make sure that if I have a non-zero class, after the restriction, I still get a non-zero class. If the class dies, then all my efforts are just vanishes. So I have to make sure this is 0. So that's what the step 1 is, to make sure that going from the cohomological class for the Galois group of F to the part where the Galois action is trivialized, this restriction map is not zero. Okay. And then I realized that I skipped a step, so very bad. Okay. So I have to apologize that somehow I have to pause that a little bit and then come back to here. Very sorry. Okay. So I guess step 2 will make sure somehow my C gets to view as a homomorphism from this to here is not zero. But now maybe I should have done this earlier, but anyway, let's do this now. That I want to interpret these conditions in terms of, looks like more like sort of the homomorphism, so in terms of elements. So evaluating of this class C on elements and see what we have. So what do we have here? So let's do the last one. Last one is easiest. What does it mean to say, okay, a global common class C, I mean, think about it as a kind of a co-cycle. What does it mean to say this restriction of the C is not zero in this class? So first of all, maybe what is this class anyways? This cohomological class is what? This is, remember, H1 of the, so this is a Frobenius V to the Z has power, right? So this, for a procyclic group, the cohomology is this quotient out by the Frobenius of V minus 1 times this space, right? And then and the restriction is basically sending this class C to its evaluation at this Frobenius element. And the restriction being now zero means that C, this Frobenius is a little bit long to write, so let me write VV from now. Okay, because I'm going to write it a lot of times later on. So I want to require that C of VV does not belong to whatever it's quotient out by, so that it's not zero. Okay, I want my CVV to be not in here. Okay, this one. What do I want from this one? Okay, I want this to have distinct eigenvalues. That's basically, there's one thing, I mean, it's not equivalent, but there's one thing that will imply is that this is not 1. I mean, it's 1 and the two eigenvalues are 1 and 1. I wanted to have order prime to P. Excuse me, prime to L. Think about this, with an element of, if this phi, right? If the row bar of phi v, this belongs to GL2 of F. Okay? There are basically, I mean, GL2F. I mean, maybe you make a quadratic extension of this. Okay. There are two possibilities. One of them, look at Jordan blocks. Look at Jordan blocks, essentially. So if one of them looks, if it looks like so, then the star will, I mean, and the order of such element will be divided by L, because the star part, you need L times to kill the star part. It's like, you know, so 1, 1, 0, 1 to the L's power finally becomes 1, 1, 0, 0. So this one has order L. So if your row bar VV equals to this, whereas the star is not 0, then this order must be divided by L. So if you want it to be sort of semi-simple, you want to rule out this case. So therefore, what's the best way to do this? So therefore, I guess if you want order to prime to L, so you don't have this sort of, I guess, the Jordan block part. And the two things on the diagonal, lambda 1, lambda 2, I guess somehow this has order, I guess, sort of, whatever the residue field, cardinality minus 1. So L to the power minus 1. So basically, you want to sort of semi-simple. It's a bad explanation. Anyway, this is sort of simple linear algebra. if the order is relative prime to L, so this is good. So this one has, we're going to use a slightly different point explanation of this. I want to say that this is the same thing as this PV is contained in the Galois group of F zeta L to the N. So here's why. Let's think about class field theory for cyclotomic fields. So maybe just do it for Q, and the general cases are similar. So think about the cyclotomic fields. So this Galois group is Z mod L to the N Z cross. Right? And I ask you, we ask ourselves, what is the image of phi v in here? Okay, phi v is the Frobenius, right? What's, how should I put this? So what's the image of Frobenius inside this Z mod L to the N Z? Well, phi v will act on the zeta Ln. I mean, just think about phi p. Just start, okay? Think about phi p. In general, it's sort of the same thing. What is sort of phi p acts on this thing? It will, or residually, it will send this to zeta Pn to the, okay, it's P inverse, accuse L to the N, right? But how is this Galois group identified with Z mod L to the NZ? It's just basically looking at the exponents here. So therefore, phi p will be mapped to P inverse in here. So that's basically what the Frobenius element, geometric Frobenius element P, what's its image in this Galois group of cyclotomic extension. And now, my condition says that basically P is congruent to 1 modulo L to the N. That's to say that this Frobenius will map trivially here. Because my condition says that this is congruent to 1 mod L to the N. So that means my Frobenius maps 1 here. Put another way, my Frobenius in the full Galois group of Q bar over Q, its image in this quotient group is trivial. That means that it belongs to the subgroup here. So that's to say this my Frobenius element is in the subgroup of Galois group of F zeta L to the N. Okay. So these are the sort of 3 conditions now I want to look at. And you can see this is an if and only relation in the sense that if this belongs to this Galois group, then this image in here is trivial. So that means your phi p is mapped to P inverse, which is the same thing as 1 modulo L to the N, and therefore P must be congruent to L to the N. So now basically we reinterpret all the 3 conditions we need in terms of just a question about the Frobenius V. And on the other side, I reinterpret this sort of the class C into a homomorphism from this class to here. Now I want to sort of make an argument now. I'll rewrite this. I'll rewrite this sort of this claim later. I'll prove this in a bit. Let's just erase it now and write the argument. The argument at this point is very easy. So step 3. Right. So basically, what do I want to do? I want to find a Frobenius element that satisfies these 3 conditions. By Chervatov density, I basically name any Frobenius element I can find a prime V, such that this element is a Frobenius for that element. Right. So now the question becomes finding an element of the Galois group as opposed to finding a prime V. Where should I find this element of the Galois group? The first one dictates that the element of the Galois group must belong to this Galois group. So therefore, we can only find it over here. Okay, we have to find some sort of element in here. as my phi v. So the idea is let's maybe, first of all, let's sort of determine its image in here, and then sort of lift it. So in fact, I will just pick any element. Practically any element. Phi inside the Galois group of d zeta L to the n over f zeta L to the n. That is non-trivial, or maybe I just pick any non-trivial elements in here that has order relatively prime to L. So just pick any element in here that has order relatively prime to L. And what I'm trying to say. And then that will automatically make sure the first one, the second one holds. And the reason we can do so is because this Galois group is large. It's like at least there's SL2FL in here. Okay? And this extension here is purely abelian. So therefore, this extension here has large image. I mean, I guess, or maybe put it this way. So from here, I mean, this part has an SL2FL here. So therefore, this whole thing will have at least a SL2FL as a Jordan-Holder factor. But SL2FL is, I mean, PSL2FL is a simple group if L is greater than or equal to 5. And this part is sort of abelian, you know, F zeta L to the n over F is a abelian group. So that will not matter. So therefore, this part, inside of this part here, there must be a, in this Jordan-Holder factor, whatever, where it is, must have a PSL-FL in it. So this must have a PSL2FL in it somewhere. Therefore, I mean, over here I have this is a huge group, so I can almost trivially find an element whose order is relatively prime to L. That's relatively easy. But now I want to lift this phi to the global thing. So I lift up, at the moment, let me lift it arbitrarily. To phi theta in the Galois group of F bar over F zeta L to the n. Okay, then I know that if I do rho bar of this phi theta, because I mean, whatever you have over here is already it's in the kernel of rho bar. So however you lift it doesn't really matter. It does not affect the image under rho bar, or maybe rho bar of phi, right? But this has order relatively prime to L. So the second condition is okay. Now I have to sort of, so basically, first condition is already did, how I choose my phi. And the second condition is done. So I have to worry about the third condition. The third condition is it's a little bit annoying. So let me move this right. So leave that space. My C belongs to here. I'm going to use this in a bit. So of course, next for 3, let me write something. So suppose that suppose that C of this phi theta already belongs to, I guess, does not belong to phi minus 1 of argument representation. Then we're done, right? So suppose not. I mean, if it doesn't belong here, then this image is not 0. Then we're done. But if phi, maybe phi, which is the action only depend on what this phi is. So phi minus 1. So suppose not. So, or like rather, suppose this doesn't hold. So namely, the evaluation of C at this phi tilde does belong to phi minus 1 of R joint rho bar circ 1. Now I want to basically pick another lift. So I want to take another one. Basically, if one of them doesn't work, you just pick another one. So I want to take another one so that it works, so that it doesn't belong to this subspace anymore. So how much can we change here? So I have C of phi tilde prime being this is a co-cycle, right? So if I change by a tau, so I'll get a tau plus tau of C of phi tilde. Right. This is a co-cycle. You must satisfy the co-cycle condition. But I want to point out that the way I change for a different lift where tau is actually belongs to Galois group of gamma zeta L. Right. So tau actually belongs to here, and therefore, sorry, not here. I mean, it's sorry. So my phi is here, and I'll lift it to the co-Galois group. So the ambiguity lies in here. So the top one. So the tau would be in here. And if it lives in the top one, it will act trivially on this rho bar. So therefore, in particular, this class C will act trivially here. So what we're doing is just basically picking a different lift. I'll just modify my original C by this C tau here. But changing this by this tau will not change anything else. For example, this first property here, for example, rho bar here, because rho bar of this tau phi. But rho bar of tau is trivial, so just rho bar of tau. The same thing. But I have the freedom to pick my lift nicely, so that I avoid this subspace here. So in the sense that we're choosing a phi here, set by 1 and 2, and then we try to lift it. And then one of the lifts doesn't work, then I just modify the lift a little. And we show that we can always do the modification so that this lift works. So what's going on here? So now basically I want to know what kind of freedom we can do to choose my tau. So this comes down to the map I just erased here. So now see so my C is really a map from the Galois group of this D of zeta L to the N to this R joint representation, right? And I want to choose a tau, so that image not in what is this? Not in sort of B minus 1 of this R joint, the subspace, whatever that subspace is. So I want to modify this cycle class by something in here, so that the image stay away from certain subspace. But now here's a catch of this SL2FL, which is that but the C here is a homomorphism from this to here. Okay, and this Galois action, this Galois group acts on this space. This is basically the standard so the way this Galois group acts on here is via the following. So this Galois group acts on this representation, basically factors through the Galois group of D over F, acts on the automorphism group of R joint representation. Oh my god. So this is, you can think of this as SL2F, roughly speaking. And this is sort of R joint representation of this automorphism group of sort of endomorphism. This is the adjoint representation of this one. And this is almost irreducible if your L is large enough. Say L is greater than or equal to 5, I think it's irreducible already. And therefore, let me finish this. So therefore, if you have a homomorphism like so, it must be surjective. If it's not 0, then it must be surjective. If you have some irreducible representation at the target, and homomorphism from something like this, it must be surjective. So the C not 0 implies that C is surjective. So therefore, you can always find out how to map to any element you pick here. In particular, you can pick an element not in the space here, and then add it on here, and then you're done. So I'll stop here and continue with the proof of the step 1 later. Okay, let's quickly give this proof here, because I don't want to spend more time on this anymore. The only piece is showing this is common 0. Basically, this again uses this condition here. We use this sort of this what's that called? The inflation restriction exact sequence to break it apart in 2 pieces. So I go from this to here. So I go the first step and then this step here. So I have Galois of and also there's some discussion that this is not equal to, so this is actually not equal to rho bar of phi, okay? But knowing that rho bar of phi has order relative prime to L, it can imply this has order relatively prime to L. I'll write the better notes in my notes. You can take a look. Or maybe let me explain it over here. So you have this rho bar here, which goes from G to GL2, and the adjoint representation bring it down to GL3. Okay? So your phi here, you go right and down to go to this rho. We know that the adjoint circ rho bar of phi has definitely order relatively prime to L. But we don't quite know yet. The image in here has order relatively prime to L. But the vertical map the kernel of the vertical map is F cross, which has order relatively prime to L. So if you have some element in here whose image here has order relatively prime to L, then this element raising to some nth power, n relatively prime to L, is 1. So therefore, this element raising to that power n must lie in this kernel, which is raising to, I guess, some sort of L minus first power or something like that, is 1. So therefore, this element has order relatively prime to L. So, sorry that there's a small issue here. I only know this has order relatively prime to L, but I don't know exactly the order is. But, yeah. Okay. Now, let's erase this. Let's do 2 parts. And let's see this part. What is this? df, maybe d over f. And this is sort of d over f. Okay. So basically, the Galois convergence of this thing can be computed by the Galois convergence of each steps by that. So this is invariant under the sub, but the sub is, the sub already keeps it invariant, so the same thing. And then this is sort of the Galois convergence of the top part, and then taking invariance under here. So let's compute each of the steps. So what is this thing here? So what is the scalar group? So this is the same thing as projected. Remember how we define this scalar group D over F. So this is sort of starting from the representation, the adjoint representation, GL3 of F, right? And this factors exactly through the Galois group of F over D. That's how I get it. So therefore, basically speaking, this Galois group of D over F. So this D over F is basically the projective image. Because when you take adjoint representation, it kills the center. So this is a projective image of this rho bar. And because my rho bar contains the SL2FL, so this roughly speaking, this is roughly something like PSL2 of some sort of F for some finite field. Maybe not the same thing as this F here, because the image might be a smaller finite fields. Roughly speaking, it's some sort of PSL F prime. So whatever whatever the first cohomology is sort of a purely group cohomology statement. So it's H1 of PSL F prime with coefficient in sort of endomorphism of sort of F. And sometimes you take the adjoint representation of this PSL2 F prime with this coefficients. Okay? You want to show this is 0. One thing we note that this is the same thing as H1 of B2, maybe with quotient by some center. Oh, quotient by some center, I guess. So I mean, maybe let me ignore the F prime thing. So let's just say all right F, so that make my life a little bit easier. Because this Borel subgroup has index in here relatively prime to L, so their H1 must be the same. And now I look at sort of the central now I somehow pass to the Borel. For the Borel part, because the order of the Borel, sort of the torus part, has order relatively prime to L. So that part can be taken out as invariance. So this thing is the same thing as H1 of 1F10 of this endomorphism of F. And then invariant under the F cross action. So you can take out the sort of the, I guess this is sort of the quotient group, quotient by the unipotent subgroup. And now this is not, again, surprisingly, this is without taking the invariance, this is not 0. But we know what it is, in the sense that because how should I say so this is a 3-dimensional space, and this thing X on the 3-dimensional space is basically something like this 1, 1, 1, 1. Oh, maybe there's a 1 here. I'm not so sure. So the action of this one on this endomorphism circ. Excuse me. So this is going to be a 3-dimensional space, and the action go. I mean, over here the base. Right. It's just, okay. So the action. So let's write down the bases here. So E1 tensor E1 dual. There's 3 bases. E1 tensor E2 dual. Trace 0 code. So wait. Or maybe it's sort of write it in terms of matrices. So the elements, one of them is this, the other one is this, and the other one is 0, 0, 1, 0. Okay? And this one conjugating this by, I'm terrible with this. If you conjugate your matrices by this. Okay, so what's the action with respect to this basis? So if I conjugate this matrix by this, I get, I want to say I get just itself, right? If I conjugate the upper triangular matrix, I must get the upper triangular matrix. So it looks like I just get it itself. But if I do this one, then I conjugate it by this 1, 1, 0, 1. I will get this, but then I will get a tiny bit in here. I'm not sure, 1 or 2. Let me not do the computation here. I didn't do this computation ahead of time. Okay, and I can conjugate by this. Then I will get something in here, maybe 1 or 2. I don't know. Maybe there's something here. I don't care. Okay? Now I want to understand what is H1 of this. So I have to quotient out by this matrix minus 1. So therefore, I left with, I want to quotient out by this matrix, the image of this matrix minus 1. So that's basically 0, 0, 0 here. And this is not 0, this is not 0. So this two of these get killed, so left with this bit here. So this is same thing as F 0, 1, 0, 0. But then don't remember that I have taken invariance under this action. But this space is not invariant under that. So 0. Okay. Sorry, I didn't do this computation, but you see that it's not 0. But as to whether it's, which number it is, I don't know. You have to do the computation. Okay, so that shows the left part is non-zero. Roughly speaking, the upshot is that it's basically this group cohomology. The question is about whether you need tight twist or not. No, I mean, like abstractly, this image is sort of this group. I'm talking about abstract groups. I'm forgetting about the sort of Galois information whatsoever. I mean, after all, it's just a group cohomology. If you don't identify with the Galois group, it's just a group cohomology. So I'm doing the group cohomology level. I think it's okay. Right. And as to what this PSL2F represent in the Galois group, there's a twist. I agree. But then I'm purely talking about group cohomology level. That's okay. Right. Good. So that part is some sort of group cohomology thingy. Now I'm going to prove, I want to prove the middle part is 0. I better prove that both sides is 0. So let's do this side. This side, the good thing is it's a hum. Because I'm taking a Galois group of something over D. So therefore, the Galois action is trivial. So now this becomes a hum. So this is a hum of the equivalent hum from the Galois group of D zeta and this going to adjoint rho bar 1. Okay? I think I can now conclude. Practically, this is a abelian. Let's look at the abelian group, right? Let's look at the abelian group. Whereas this is under our assumption, this is an irreducible representation of the Galois group of D over F, because of the sort of PSL to FL thing. Even the adjoint representation, I think, is irreducible. Now you have an abelian group. At best, it will generate. And this action of Galois group on this one is vectored through a character. So therefore, I guess this is a one-dimensional thing. This is a three-dimensional irreducible representation. There's no hum between them. So we're done. Whew. So that's a rough idea of how this is done. So let me come back to this. So we assume that the image of the roll bar contains SL2FL to simplify all of our sort of discussions. But you see that if this doesn't hold, there are lots of places need to be modified for each of the computations basically here. So you have to basically enlist all possible images and then compute, so for each image, what sort of this cohomony looks like, and why this is 0, and same here, why that's 0. Just a separate argument. Some of them doesn't work, then you have to rule them out. So it's a bit of a mess. So I don't think it's a very illuminating argument. So let me just sort of assume this and then make the argument a little bit shorter in that sense, but a stronger assumption. But unfortunately, in application, we will have to use the case L equals 3. But you have to take in faith that this, whatever the argument we just run goes through. So this is always 0 in all the applications we use. And there was another usage of that somewhere, somehow showing that this thing has large image in here. That's also a kind of a case-by-case argument when L equals 3. But I don't want to present that here. Okay. Now, let's move on to happy stuff. I want to talk about local deformation. Okay, local deformation conditions. So let's sort of talk about. So basically, so far we haven't imposed any additional assumptions except whether a prime is unramified or ramified. So now I want to talk about sort of more general things. Like if you have a global Gauss representation, I want at some places it has sort of deformation allowed of certain type, and other places allow it for a different type. For example, especially the prime dividing L. If you have heard the word sort of Piat-Hawk theory, like I want the deformation to be crystalline, or I want the deformation to be de Rham, or whatever. So those are I'm just going to discuss a general framework for discussing such things, and right. So let's keep this notation as before. And gamma is a profinite group. Let's do a general theory. The finiteness condition. There was a finiteness condition for H1. Suppose it satisfies that. And I start with a general representation. If I fix determinant, I will ensure that L does not divide N, as I just corrected today. So once we have this data, I'll have a deformation ring. And I like to think of this as, so if I think of this as a formal scheme, this will carry an action of PGL and hat, right, by conjugation. A local condition is a PGLN stable closed ideal. I think it's automatically closed because this deformation ring is no theorem, so it's automatically closed. It's a PGLN stable closed ideal of this deformation ring. Or equivalently, I think of this as a subscheme. Geometrically, SPUF F. That is stable PGLN action. I want to maybe clarify a little bit of the what I mean by this PGL unstableness. So in literature, there are two versions of, well, there are basically only one version. Not the version I like to use. Anyway, so let me say that what's the version in literature first. In the literature, it's often written in terms of pointwise version. But I guess it's helpful in the sense that this version in application is easier to verify. It's the following. So if you think about every element A meaning that you have some sort of matrices. If you have some sort of matrices and you quotient out by the scalar, for every such element, if you conjugate your universal representation by this A, you can conjugate it by it. So this is a different lift, right? Of rho bar. So whenever you have a different lift of rho bar by universal properties of this deformation ring, you will get a, let me write FA of R rho bar frame to R rho bar frame. Right? By universal property of this of the rho bar. I mean, it's not, this is again, sorry, this was a universal object, and you have a new representation with image in here, with sort of GLN of this one. So whenever you have a different lifts, you have a homomorphism from the universal one to that one. So that's the action. And obviously, this, by the uniqueness of such homomorphism, this is a group. So this defines the action. So this defines the action. Of PGLN hat of R rho bar frame on. So for each element in here, if you take the, I guess for each element in A here, you can act on that. Satisfying the correct group law. Right. So the stability condition I was talking about here, we should say pointwise. Stability condition is to say that somehow for all such FA will take the ideal I to I. This is actually equality. But the condition, maybe just condition really is take I to I. Then you take inverse to bring it back. So it's isomorph. This first version. The second version is that I want to think of this in sort of scheme theoretic version. In the sense that I have a morphism from PGLN cross buff I have a scheme theoretical sort of action. I think of it as sort of formal schemes multiplied together and then map into another formal scheme. And once I have this, I can look at how it acts on the rings. That means I can sort of pull it back. It doesn't matter the order. Let me just write the order this way. It doesn't really. Right? If I map on the schemes and then you pull it back to the functions. And the condition is that. So this condition is that pulling back the ideal belongs to ideal complete tensor with OPGLN. Okay. let me point out that 2 implies 1, but not conversely in general. That's because for every A, so this condition here is this is some sort of universal. You should think of it as sort of universal stable in some sense. That one's sort of pointwise stable, in the sense that for given element A in PGLN hat R row bar frame, right? This is the same thing as giving a homomorphism from given sort of R row bar frame point of this thing. It's equivalent to giving a homomorphism from A, maybe call A star, from O PGL and to R row bar frame. That's the same thing, right? And then if you have this sort of, how should I put this? So you have somehow this condition here. So how do you get the sort of pointwise condition from this? The relation between the sort of universal one and the pointwise one is that somehow you have, right, leave something here. So you have this sort of this A here, or the A here. I want to say this, but or maybe put it right down here. So this A will define a so this A will be somehow a map from SPIF R row bar frame to that one. And then this one has a diagonal thing into that. If you unwind all the definitions, this composition is the action by A. So this is sort of universal action, and then you take a point in here, and that defines a map from this crosses into here, and you take the diagonal of spec row bar frame into here. So that composition is precisely the action by A. And now suppose that you know that action star of Y belongs to here. That basically was clear. Sorry, I didn't prepare this, so it was clear to me. So action star. So suppose that we know this, right? Now what I want to know is that, so this is FA. So I want to know what, so suppose I want to know what FA star is. Suppose I know this. Then FA star will be the same thing as writing as some sort of composition, right? Delta star of, hold on a second, several steps. A tensor with one star, and then X star of I. Right? But then this is the same thing as delta star of a tensor. This is sort of in I'll have to do O first to line it up well. Right? And just pulling this back, you get R row bar frame tensor with I. And this delta star is basically multiply all of them together, so this is just I. Well, I mean, maybe over here you need to contain it. But anyways, it's going to be equal. So therefore, FA star is equal to. So in a sense, if you know the universally act pull back belongs to here, you know that for every point, it maps this ideal to this ideal. but it doesn't go the other way. Somehow remark is that 1 implies 2 needs, I think needs R row bar frame to be reduced. Small subtlety. Let me give you a typical example. Of why I want to sort of think about this local conditions stuff. I want to start with the unramified local Galois representation. So the Frobenius phi goes to a matrix 1, 0, 0, p. But I want p to be not congruent to 1 mod L. And this is actually one of your exercises. But let me search. Depending on my time, whether I will do it or not later on. But your calculation should show that. Let's sort of look at the general frame deformation of this one. Or you know what? Let me just give you the answer. I'm not going to do the details. If you want to know the details, you should work on the problem yourself. So, or I wrote it up in my notes. So the deformation ring formally looks like so. Okay. So what does these variables represent? Somehow the row universal of phi at p is, as before, we can, because residually we have two distinct eigenvalues, I can lift this residually distinct eigenvalues to, I guess, eigenvectors to global eigenvectors in general. So I can lift them as so. Always. So when I know what the eigenvectors are, then eigenvalues are these two. And eigenvectors, we did a Hessel lemma last time. So row universal phi p must look like that. And also we have to deal with the time inertia in case there's possible time inertia here, which is 1x, y1. And you can show that time inertia. So this takes a little bit of time, but then not that difficult to show that the time inertia must look like there's some b here. Possibly there's some b here. This is purely because the ratio of this is 1 and p. You're allowed to have some b here. Now so whenever you have these two, let's check what the conditions. So it takes some time to show these can only be 1s, has to be 0. Okay? I'm not going to skip all that. So you have some b here. But then I need some condition that U universal. Let me just write it. So because you want this to be tau to the p. And that's a relation between the Frobenius and the time generator tau. If you spell it out, what it means that 1 minus s inverse p plus t inverse tau being 1, 1b, 1 plus s p plus t is equal to 1, 1. To the p's power, just pb, nothing else. Now let's do a linear algebra. So what do I do? What do I have? So I have p plus t. Right? Yeah. So note that somehow my conjugation is the other way around. Let's see. I have p plus t over 1 plus s times b equals pb. Right. If I conjugate it by diagonal matrices, somehow on the diagonal I have no relations. I mean, this is basically how I show that two diagonal things are in some sense just one. And the upper right triangle, upper right point, I have sort of p plus t over 1 plus s. Now I multiply this over and then kill the things I don't like. So I have tb. Okay, maybe I just write it down. It's not that bad. Right? I multiply this over and expand it out. PB kills each other. So I have that. So B times PS minus T, T minus T, doesn't matter. So that's the only relation I need. So what do I want to say about these? Let's analyze what's not, okay, we have some sort of explicit example of this deformation ring. Now let's analyze what each variable means and how the action of this sort of conjugation. What's the action of PDLN action on this space looks like. Let's make a couple of remarks about this. So first of all, PDLN action on this deformation ring is purely on x and y variable. Why is that? I mean, somehow you're acting on a representation by conjugation. Such action will not change eigenvalues. It will only change eigenvectors, right? So eigenvectors is precisely 1x and y1. So basically that's where you're changing. You're not changing anything else. Of course, it's a little difficult to write down what x and y, and maybe variable and possibly scales b, because this b is about sort of the ratio of the length of two eigenvectors that you can get by conjugation. You can change that. But these eigenvalues you can't touch because conjugation doesn't change eigenvalues. Okay, so that's one thing. But you only scale b. You don't get to change whether b is 0 or not. That's the thing. What does it look like? So, I mean, forget about sort of the variables that doesn't sort of appear here. This looks like something like, in my mind, this looks like sort of small x, small y, quotient by the equation xy equals 0, right? I mean, this is, say, small x. This is small y. All linear terms, you can change a variable. For example, I guess t being ps plus the original t or something. So that looks like this. So therefore, the spectrum this looks like two components. There are two components here, x and y, right? X, y. So one of the component is defined by the equation b being, let me see, which one do I want first? So let's do one component defined by b equals 0. The other component is defined by t equals ps, and typically b not 0, right? That's how we visualize this deformation space. I mean, suppose it should be sort of big dimensional, higher dimensional planes. I'm just going to draw this, ignoring all these sort of formally smooth factors. So what is the component about b equals 0? So this component looks like r row bar frame over b. If you kill b, what is b here? B means this tau here. If b equals 0, then this is an identity matrix, so therefore the tau is trivial. And therefore you're deforming your Gaultier into an unramified part. So this is maybe I should say r row bar frame unramified. I think I introduced this last time somehow. So I have one component where the deformation is purely unramified. Since I kind of assume that you already kind of, I guess for those who heard a little bit of modular forms, well, I don't know how I'm going to do that later on. But this will correspond to modular forms with level n, but p does not divide n. if P does not divide N, the associated Galois representation will be unramified at P. So whatever the Galois representation associated from whatever the Galois representation that's associated to these type of module forms will have image on this red ones. The other component is usually right. I mean, just quotient by the other equation, T minus PS. This is a little strange if you look at it in the sense that if T equals PS, so over here, let me give it a name. It's called R row bar frame Steinberg. Short for Steinberg. We'll see. We'll say what it means in a bit. So, what's special about this? Special about this is the two forbidden eigenvalues have ratio exactly equal to P. That's because T equals PS, right? So T is PS. So if you replace T by PS, so this is P times 1 plus S. Right? If T is PS, then this is P times 1 plus S. Okay? So the ratio of two forbidden eigenvalues is precisely P. If you think about this actually breaks, if you have heard of this, this actually breaks the Ramanujan conjecture. The Ramanujan conjecture says that the two forbidden eigenvalues should be have real absolute value the same number. But now the ratio is precisely P. This breaks it. So this is something special. So this will correspond to modular forms with level precisely Pn, and P does not divide N. But in the level, there's precisely 1 P in that. And it is so-called P new. Namely, it doesn't come from a modular form which has level N away, level away from P. So all such forms has a property that the associated Galois representation, the Frobenius, there are two eigenvalues. The ratio is P. So this is so-called Steinberg component. So for our application, in some sense, it might be useful to sometimes consider, okay, only forms correspond to the first type, or only the form corresponds to the second type. I'm just taking an example to illustrate this. Of course, in general, you should imagine there are more irreducible components that will correspond to, in terms of modular form size, different structures of the level, or structure of condition on the level. So that's what we're doing here. And also, let me point out that the way we characterize this is by asking whether B equals 0 or not, or T and S. So all of these conditions are invariant under the PGLN action. So maybe I should say, okay, this is going to be some sort of condition. This is sort of the ideal that defines it. This is the ideal defines the other one. So we have separate conditions here.